So this is a video on centripetal forces. We need to identify what the centripetal force is in each situation, and then you need to realize that the net force directed towards the center of the circle can be let equal to the centripetal force formula. So it's, as it says on the screen there, it's a force that exists in the system already, and if it exists in the system, it makes the body continue to move in a circle, and then once we know what the centripetal force is, we can leave it equal to mv squared over r. Okay, so let's start with 6 scenarios. On the left hand side there, we have a motorbike going around in a circle, and we need to identify what is the force allowing that to go around in a circle. Now the force will be directed towards the center of the circle, and in this particular instance it'll be the friction of the friction between the tires and the ground. If we look at the right hand side, we have a satellite orbiting the Earth. The satellite has a force acting on it directed towards the center of the Earth. It's the weight of the satellite, so that's the centripetal force in that case. So again, what force is directed towards the center of the Earth? It is the weight, so we leave the weight equal to mv squared over r. In the left hand side, friction would be the force directed towards the center, so friction would be mv squared over r. Okay, if we look at the right hand side, we have a wall of death. So that cylinder is spinning, the person is in contact with the wall, and they're affixed to the wall, so they're not allowed to slide down at all. Now because the person is in contact with the wall is pushing back, so we have a reaction force directed towards the center of the circular motion. That's a horizontal reaction, so the reaction we would let equal to mv squared over r in that case. On the left hand side, it's almost identical to the motorbike going around the track. Friction is what's responsible for keeping the person moving in a circle, so friction, that force could be let equal to mv squared over r. And we have 2 other cases. So on the right hand side, we have a mass being suspended with a string. So the forces acting on the mass are the weight vertically downwards, and if there's a string attached to it, there's a tension away from the particle along the line of the string. Now neither of those are directed towards the center of the circle. The weight is perpendicular to that direction, so the weight will have no centripetal component, but we can resolve the tension into a component that is towards the center of the circular motion. So it's a component of the tension creates the centripetal force in this case. On the left hand side then, we have a connected particles problem. We have 2 particles and the string is taut, so there's a tension acting on both of those particles. If the mass hanging underneath is at rest, then the weight of it, m2 by g, equals the tension upwards, and that tension is the same tension acting on the puck on top of the table. Now they've called the tension R there, we'll roll with that, and that particular tension there is the centripetal force. So the tension, which equals m2 by g, would be let equal to mv squared over r.